Okay, the subsequent question asks that we integrate the same gradient dotted with the dr along the unit square from 0, 0 to 1, 0 to 1, 1, from 0, 0 to 0, 1 to 1, 1 to 1, 0, and back to 0, 0. So I'm going to call these four segments of the path, path 1, path 2, path 3, and path 4. Put these together, you have the whole loop. Okay, on path 1, which goes from here to here, how do we parameterize that? Well, the y is always equal to t. I'm sorry. I mean, yeah, we can do that, but the x is always 0 from here to here. Just as the y value is always 1 on path 2, the x value always 1 on path 3, and the y value always 0 on path 4. That should be clear. So as we go along this path, we're going to let y equal t. We're going to let t go from 0 to 1. And we'll get an integral along this path. On path 2, as I said, and it should be clear that y is 1, and we can let x equal t. As t goes from 0 to 1, then x will go from 0 to 1, so that's going to give us path 2. On path 3, x is going to be equal to 1, and we're going to let y equal 1 minus t, so that when y is 0, when t is 0, y is going to equal 1. So we're going to be up here at the point x is 1, y is 1. That's going to be the point 1, 1. And that's going to bring us down, by the time t equals 1, to the point x is still 1, but y is going to be 0. That's going to give us this point. And it should be clear that that's a parameterization of this line segment. And similarly, the fourth line segment, we're going to let x be 1 minus t, so x starts at 1 and ends up at 0 as t goes from 0 to 1. And y remains 0 on this whole path. And again, t goes from 0 to 1. Now it's convenient to have t going from 0 to 1 on each path, because then I don't have to write out, it's going to turn out I won't have to write out 4 different integrals. Since I'll have the same limits on every integral, I can just combine all the integrals into one. So on 1, we can go to, specify our r of t function. R of t is going to be tj, because of course y is t and it's y times j. Okay, so r is tj. On the second, r is ti plus j. Why ti plus j? Well, a vector from the origin out to a point on this line will have a y component of 1 and an x component that'll be equal to t. Okay, so this is the vector, j plus ti. Now, j is always just j, so that the vector is always just 1 unit up in the y direction, and t goes from 0 to 1. That'll take the vector from here to here. We'll trace out this line segment. So that's our r of t. Then, without going into detail, r of t for the third segment, and you should be able to figure this out, is just going to be I plus 1 minus t times j. Looks like I have an extra parenthesis there. And on the fourth interval, r is going to be just plain old I times 1 minus t. So what's our dr? Our dr for the first interval, well, we just do dr for each of these, and I'll read them to you. J dt, okay, derivative of this is just plain old j. Derivative here is just plain old I, so it's I dt. On 3, it's negative j dt. On 4, it's negative I dt. So, for example, on the third interval, what's our direction of motion? It's the negative j direction. Right there we have it. Our dr is negative j times dt. Then, I haven't written this out for every interval, but on the second interval, just to pick one, dr is I dt. And del f is what we get when we substitute the corresponding values of x and y, x being equal to t. You can tell that from the r of t function, and you can see that here too. And y equal 1. That 1 being the coefficient of j, 1 being what y is equal. So you can understand that in a variety of ways. So what we're going to do is we're going to say, well, okay, on that part of the curve, all our x values are going to be replaced by t, because x equals t. So the x's here are all replaced by t. And y's are always 1. So all our y's get replaced by 1, and you can verify that if we do that with our del f function. I don't know if you can see the del f over here, but you should be able to see the entire del f function that we just used, so hopefully you're familiar with that. We get this, e to the t cosine t minus e to the t sine t times I minus e to the t sine t j. Okay, then del f dot dr. Well, our dr is just I dt, so and I wrote that down wrong. Okay. I apparently was on a roll. Okay, del f dot dr, this would be del f dot r. Dr for r equal to ti plus j is I dt. So that when we do this dot product, we just pick out the I component. It's multiplied by the I component here, and we simply end up with not quite exactly what I said. Where in the world did I get a t e to the t? Because there's no t. Well, it's because I dotted it with what I'd written. And it's just plain not right. Okay, so we'll do the dot product. Del f dot dr is just then this dotted with I dt. I dot I is 1, so we just get this. And that's e to the t cosine t minus e to the t sine t. So that our integral will become the integral of del f dot dr over path 2 will be the integral from t equals 0 to 1 of this expression. And I left off the dt here, still being careless. The integral of this expression, e to the t cosine t minus e to the t sine t dt. That's the integral over path 2. The integrals over paths 1, 3, and 4 are set up by going through the same steps and doing them more carefully than I did. Another error, I didn't put an arrow over my I there. Let's be careful about that. Okay. Now all this stuff about eigenvectors isn't part of your course. Don't worry about it. It's part of linear algebra, and I was running short on board space, so I kind of had to overlap. So if you do these integrals, write down all 4 of them, a lot of stuff's going to cancel out. And you should end up with 0.